Okay, it's time to look at two other forces that are very common, both in your life and in physics. And we've actually already mentioned both of them. The first one is the one that's acting on you right now. So whatever it is you're sitting on, your weight, Fg, is acting down, and the object that you're sitting on is putting a force upward. This force is what we call the normal. Is it just me or is that blurry? Now it's really blurry. The normal force. And so it's a capital N, capital F with a subscript N. Okay, so this is the normal force. So it's the force of the second surface pushing back on the first one, right? So if this is a block or a box sitting on the surface, the weight of the block is acting downward, and so that's the Fg, and so the surface is pushing back up. So we say it's the force that the second surface is putting on the first surface as a result of the object. Now, the normal force, the word normal in math and in physics means perpendicular. So, like in math, they might say draw a normal to the surface. It means draw a perpendicular line to the surface. So this normal force is always, 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 always perpendicular to the surfaces in contact. Always, 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 always. Okay? And the bigger the normal force, the more closely together, more pushed together the two surfaces are. Okay, so the normal force is the force of the second surface pushing back on the first, and it's always perpendicular to the forces in surfaces in contact. In this particular case, Fn is going to equal Fg. Assuming this object is just sitting there, just like you, then the object isn't moving, so if we did F net in the y direction is equal to MAY, and this is why I use sum of the forces in the y, just because I don't really like a whole sentence as a subscript. So if we did the sum of the forces, it would be Fn going up minus Fg going down, and because the box isn't moving, the A is 0, so the MA is 0. So F net will be equal to Fg, okay? But that is not always the case. It is in this particular situation, but imagine that you have that box again sitting on the surface with the Fg acting down and the Fn acting up. But imagine now you want to move the box across the floor and you want to do it as easily as possible, so you tie a string around the box and you pull upward at an angle on the string. So this is the force you're applying. This force going upward at an angle is going to have a component in the x direction that's going to move the box forward, but it's also going to have an upward component that's going to take some of the weight off the floor. In other words, the floor isn't going to have to push back with as big an Fn as it did. So if we did some of the forces in the y this time, you're not actually lifting the box up, but it would be Fn plus your Fy minus the Fg equals 0. So this time, the Fn would equal the Fg comes over and it's positive minus the Fy. So the force that the floor has to push back with isn't going to be as big as it was up here because you're helping. If you were going grocery shopping, and this is your shopping cart, Fg is acting down, Fn is acting up, but when you push on your shopping cart, you push downward at an angle, which means this force you're putting has an x component and a y component, and now this time the Fn is going to have to be bigger than Fg because it has to also allow for the force you're pushing down with. So if we look at all the forces in the y, the shopping cart isn't flying up into the air or sinking through the floor, so it's not moving in the y, but we would have Fn minus Fy because it's going down, minus Fg equals 0. And if you rearrange for Fn, it will be Fg plus Fy. So now the Fn has to be bigger than what it was up here when there were no other forces because of the force you're putting down. And then sometimes it looks like Fn isn't connected to Fg at all. Imagine picking up your textbook and holding it against the wall in your house. So you're putting a force inward on the book, on the wall, and the normal force will be coming out like this, okay? Whereas Fg would be acting down. And if you don't push with the big enough force in, this book will actually slide down the wall, and you might want to try it because it's really pretty cool. The more force you put in, the less it'll slide down the wall. But if it's not sliding down the wall, it means there has to be another force acting upward, and there is. That force is friction. And the experiment I just talked about you doing, pushing in with a bigger force, which makes the Fn bigger, actually shows us that friction and the normal force are connected to each other. Okay, and we're going to go to friction right now, but first, just to recap then, the normal force is the force of the second surface pushing back on the first surface as a result of the first surface putting some force. Okay, sometimes equal to Fg, but not always. And so we can't say that, but always, always, always perpendicular to the surfaces in contact. Okay, so that's the normal force. Then friction. Friction is a capital F and for some reason with a small fr. Okay? And friction is really like a surface's protest to an object trying to move over it. So if I push an object in some direction like this, friction will always oppose it. So friction always opposes motion or the desired direction of motion. Opposes motion or desired direction of motion. And what I mean by that desired direction of motion is sometimes the object isn't moving, but it wants to, but friction won't let it. So imagine you have a ramp with a box on the ramp. You should be able to imagine that if this ramp is really slippery or steep enough, that the box would move down the ramp. If the box isn't moving down the ramp, because it wants to, everything always wants to move to its lowest possible location, and so if it isn't moving down the ramp, it must be because friction is acting up the ramp to prevent it. So it's not moving, but friction is still acting on it, and it's opposing the direction, the desired direction of motion. Okay, so friction always opposes motion or the desired direction of motion. A second important thing about friction is that all surfaces have some friction. All surfaces have some friction. Now we can polish the surface, we can Zamboni the surface, it's still going to have a little bit of friction. We can't get rid of friction completely. Obviously, the smoother, the more polished the surface, the less friction there is. But there are companies in the world that spend zillions, billions of dollars trying to get materials that have no frictions. One of those companies is companies that make roller coasters, because the less friction a roller coaster has, the longer the ride and the faster the speed, and therefore the more money the company would make because more people would come to go on that ride. Okay, so all surfaces have some friction. And how much friction an object experiences is directly connected to how closely together the two surfaces are, how much they're pushed together. So imagine that you're sitting on a toboggan and someone's pulling you across the snow. And or maybe you're pulling a little kid, and it moves really quite easily. But if I put another person in this toboggan, which causes the Fg to be bigger and the Fn to be bigger, now the two surfaces are squished closer together.